So what we've looked at is the reactions of the alkenes, the alcohols, the alkyl halides, the amines, and now what we want to do is look at the aldehydes and ketones, the carboxylic acids and derivatives. Hi Johnny, yes. And then hopefully we'll get to the condensation, polymers and reaction schemes. And then you would have done all the organic. That's going to be asked in the exam. So, aldehydes, remember what those 7 tips. It helps if you look to see what's going to be the reactive site and so how it's going to react. It helps you remember what sort of reagents. So you've got that carbon that's attached to a double bond or double bonded to an oxygen. So the carbon is fairly electropositive because of the electronegative oxygen. So it's going to undergo those sort of reactions. Now, because of this double bond, we focus, there's a lot more reactions that aldehydes do, but we focus pretty much only on the oxidation and reduction. Now remember I said oxidation as far as organic chemistry goes is removing hydrogen or adding oxygen. And if you have got a hydrogen attached to this carbon, it can, or the reactive site, then it can undergo the oxidation. So if I do this, these are both under reflux, okay, so I'm trying to make sure that it goes all the way, I will get to the carboxylic acid. So you can see I've removed that hydrogen and I've added an OH. So that has been oxidized. Hopefully by now you've recognized that this is a good oxidant. Dichromate and permanganate are both good oxidants and they'll always oxidize. So that's the first reaction you have to learn. Now this can happen with really any oxidant and we'll look at a few later, but permanganate and dichromate ones are the common ones. We can also use other ones like silver ions, Ag+, and copper 2+, and we'll see that just now. Now remember, although you've learned the dichromate as part of your redox reactions, you could be asked to identify, you get a reaction scheme and then you get told, how would you identify that this is an aldehyde? So obviously one thing is aldehydes will react with dichromate and form an acid, so it'll change the orange dichromate to the green chromium ion to form a substance that will be acidic. By the way, remember this is acidic, so don't say you can then test the reaction mixture and it'll turn red, the litmus paper red, because obviously it will because it's acidic. But once you've isolated the product will be acidic. Okay, and a quick and easy way to see if something is acidic is to react it with a carbonate. So you add sodium hydrogen carbonate or sodium carbonate. What would happen if you added sodium hydrogen carbonate or sodium carbonate to a carboxylic acid? Thinking back to level 1 chemistry, and you did a bit of it in level 2, acid plus carbonate gives salt plus water plus carbon dioxide, correct. Okay, so you're going to see fizzing. So that's a quick and easy test. And as I say, they do ask a lot of tests, or they might give you a test in a reaction scheme, and by identifying what that test is for, you know what that compound is you're supposed to have worked out in the reaction scheme. And when we do reaction schemes, you'll see what I mean. The other part is we can also make aldehydes undergo reduction. So if that's my aldehyde, remember it's either adding, if we're reducing something, we're removing oxygen or adding hydrogen. So there's my hydrogen's already got, and I can add another hydrogen. So it's been reduced, and sodium borohydride is the one we use there. So the hydrogen here is in the form of hydride. It's actually H minus rather than H plus, and then that adds on. Again, remember thinking, I've said H minus, so that's negatively charged, and you can see why it's going to be attracted to a more positive carbon. Okay, so those are the two reactions for aldehydes. Where aldehydes, you always get a primary alcohol. Why? Because this is something you also need to know. So John, I see is typing, and Caleb, and quite a few of you now. Okay, the O must be attached to the end because it's an aldehyde, yes. Because the aldehyde's always at the end, the alcohol formed is going to be at the end. Yes, thing at the end. As long as you don't write that in the exam, but yes, the aldehyde group is always at the end, so the OH will always be on the end carbon, or the terminal carbon, if you want to use good chemistry words. If you have a ketone, ketones can undergo reduction, but they can't undergo oxidation. Why not? What is missing in a ketone? So see, John is typing. Right, it can't form more bonds to this. Right, there's got two there, plus this carbon-carbon, plus that carbon-carbon. And remember, those bonds are quite strong. And there's not really a difference to make it get going. So there's no hydrogen bonded to here. There's nothing more that you can remove, so you can't oxidize this further. Like you can't add an OH to this carbon. Okay, so it can only be reduced, so we use sodium borohydride again, and you will get only secondary alcohols because the ketone carbonyl-carbon is always between two other R groups. This is an alkyl group, and that's an alkyl group. So ketones get reduced to secondary alcohols, aldehydes get reduced to primary alcohols. And again, that's important depending on how the question is asked. Okay, and we've already answered that question. They only undergo reduction and not oxidation. As I say, aldehydes and ketones, there's lots of other reactions they can do, but you don't have to learn them for level 2, so that's fine. What you do need to know, though, is the identification tests. So using the dichromate is one of them, okay? Remember that dichromate is an oxidizing agent, so it will react with an aldehyde, but not with a ketone, because a ketone won't can't get oxidized. So one of the things, if you get asked, you get formed these two different products, how can you distinguish whether it's an aldehyde or a ketone? Using dichromate could be one of them, because if the orange color turns green, then it'll be an aldehyde. And if it doesn't, it'll be a ketone or something else. Try that. What if the answer I've sort of given there is very much sort of like an achieved level. Depending on how the question gets asked, you might have to give more reaction conditions, like you might have to say it's acidified. So again, I strongly recommend that you watch these videos just to help you sort of become aware of these reactions. The other one is the Tollens reagent, and that's the one with silver nitrate, and you form, it's also called the silver mirror test. So it's either called Tollens reagent or silver mirror, and if I go all the way to the end, you can see, okay, can you see it's being warmed up in a warm water bath, and that will turn silver, because what's happening, the aldehyde is again being oxidized. In this case, the silver is acting as an oxidant, the Ag+, and it's taking an electron from the aldehyde and becoming Ag metal, and then the silver metal sort of stays on the surface. Okay, then the final one as a test is using Felling's reagent. Benedict's solution is pretty much identical. It's really the copper 2 plus ion, which I think you know is blue. And if you move it along, I'll be showing these again. You can see the blue color. And it goes at brick red. That is the copper 1 plus substance. So again, aldehydes will do this, ketones won't, because all of these are oxidizing reactions where you're oxidizing an aldehyde and a ketone won't. Okay, here the same thing. So I'm not going to do these again, but you can see that lovely silver mirror there, and you can see your copper 2 plus, which is blue, going to the copper 1 plus, which is this brick red precipitate. Okay, so those tests you do need to have to know. Okay, so what I've got up here are all the reactions we've done so far. You can see alkenes have got a lot of reactions. There were really just those 4 plus the 2 tests. Okay, the haloalkanes, you could go to the alkenes and the alcohols and make primary and secondary amines if you react them with ammonia, alcoholic ammonia, and not aqueous ammonia. And if you react it with an amine, it'll become a secondary amine. And then your alcohols, you can have an elimination reaction to form an alkene, or you could do a substitution reaction where you remove the OH and add a Cl or a Br or something like that. Now I have got here HBr and HCl. They're not actually very good to go from a primary alcohol to a haloalkane or a secondary alcohol to a haloalkane. SOCl2 is a much better one. So, highlight this in your booklets, SOCl2. Those sort of are accepted, but actually they don't do very well. Now, Caleb, you've got a question mark there. Okay, sorry, you've got the haloalkanes with non-alcoholic. If you've got aqueous ammonia, then what you form is an hydroxide. Because your NH3 now becomes NH4 plus, it's not a nucleophile anymore. So the OH minus becomes a nucleophile. So you'd get the alcohol. So instead of forming the amine, you would go and form the alcohol. So, because here, can you see the OH minus aqueous goes, the OH minus becomes the nucleophile to attack the haloalkane, and so it forms a secondary or primary alcohol, depending on what this is, and not the amine. Okay, alcohols form aldehydes and ketones, and aldehydes you can go further to carboxylic acids. And then one which we haven't discussed directly now, and we'll do a little bit later, is we can react a primary amine with a carboxylic acid to form an amide. Okay, so that's quite a lot to learn. As I say, learn it by reaction type. That's why I've tried to highlight these in different colors: substitution, addition, elimination, oxidation, reduction, and acid base. As well as learning it by reactant. So sodium borohydride, where would I use sodium borohydride? Where would I use concentrated sulfuric acid? Okay, with water or without, just conc sulfuric acid and heat. So all those sort of things, try and learn it in different ways. And these are just the numbers if you wanted to learn how many you have to remember. I think it was 16, okay, going back, and it was 15. So you've learned 15 reactions so far, so you're doing well. Okay, any questions on that? Nope, okay. So let's have a quick look. And as I say, when you learn reactions, try and do examples where you go from an unknown to a product or from a known to a product. So here I've got sodium borohydride forming a secondary alcohol. What sort of functional group do I need to make a secondary alcohol? Now, an aldehyde will form a primary alcohol. So yeah, and that's why, you know, the more you sort of practice like this, the more you'll the ketone, and so the ketone is where, uh, you know, as I say, go to where the functional group is. So this is the carbon that is the reactive center on this side. So that is the carbon that had reacted. Okay, so my ketone, propanone, with sodium borohydride becomes propane 2-ol. Okay, here I'm going forwards to an unknown. So I've got an amine reacting with a alkyl halide. So what am I going to form? This is a primary amine with an alkyl halide. Well, we've got a haloalkane, so we're actually forming a secondary amine. You learnt it as an alkyl halide with a primary amine forms a secondary amine. Now here I've made this the major thing, and I've made that as a reactant. So can you see that methyl there is added on here, and this propyl group here is that propyl group there. So a primary amine and an alkyl halide forms, or haloalkane forms a secondary amine. And you do not have to learn the naming of a secondary amine. Right, here I've got an OH, so I've formed an alcohol, and I've used conch sulfuric acid and water. So what did I have here? Great, okay, an alkene, and not a haloalkane. Remember, from a haloalkane, it was a hydroxide. So with the acid, it comes from the alkene. And finally, SOCl2, what would I use? Yep, an alcohol. Okay, and it would actually be a secondary alcohol because it's this carbon that has the Cl on it. If the Cl was on this one, then it would have been a primary alcohol. Okay, SOCl2 works with any alcohol, tertiary, secondary, primary, but it's just because the Cl was there. Okay, right, so that's, you know, we're now on the last lot of reactants, and so it's the carboxylic acids and their derivatives. So if you have a look at the reactive center, with carboxylic acids we've got two reactive centers. It can react as an acid, obviously, carboxylic acid, acidic, which means an acid is a proton donor. So it loses a proton, it loses an H+, and I hope you all know it loses this H+. So you're left with RCOO- as the anion. So it can react as an acid. So if you put it together with an amine base or any other amine, like, you know, sodium hydrogen carbonate or something like that, it'll react as a straightforward acid. It also is susceptible to nucleophiles because I've got this very electronegative oxygen here as well as there. So it might get some electrons supplied in by the alkyl group, but you've got lots of electron density being sucked out of it, so it's pretty electropositive. So nucleophiles are going to try and attack it. So anything that's rich in electrons, got lone pairs of electrons, or negatively charged is going to attack. Okay, so we can have substitution if it attacks this carbon, okay, and it kicks out the OH. So remember, if it comes in here to the carbon, it's going to remove this whole OH group. It's going to cut there, or it'll be an acid base where that bond breaks. So I've got two places where the bond can break, the CO bond or the OH, depending on whether it's an either substitution or an acid base reaction. So here, in terms of a substitution, conch ammonia, again, I don't want to have lots of water around because water allows you to have OH minus being produced. I mean, ammonia in water will produce OH minus. And if I've got OH minus, I'm just going to form the carboxylic acid straight back again. So concentrated ammonia, alcoholic ammonia, what will happen is that will attack as my nucleophile because I've got a lone pair of electrons in my ammonia, and then I'm going to form my amide. So carboxylic acids in conc alcoholic ammonia will form an amide. If I just added ethanoic acid to ammonia, and I don't do any heating or anything like that, I'm going to get a straightforward acid-base reaction. Okay, but if I treat it in more severe conditions where I remove any OH minus that could be around, I can form the amide. Okay, so the leaving group is water, and that's also why I don't want water around, because I want to try and remove all the water that's being formed to drive the reaction to the right. Yep, okay. And then the other one is the acid base. So if I have ammonia, but now if it's aqueous ammonia, then it's going to be a straightforward remove the proton, form the ammonium cation and the ethanoate anion. So are those two types of reactions clear? Yeah. So just be careful when you say, you form an amide by reacting with a base. Be very clear that you have it in the concentrated one, alcoholic, no aqueous around. This one can be aqueous. Okay. Right, so here again is the sodium carbonate. It's a good simple test to do, and so I'm just going to drag it along very quickly. Okay, so I don't know if you can see the bubbling. Oops, where did the test tube go? I'm just trying to see. Oh, okay, now he's just checking for the lime water. So have a look at this. So what he's doing, he's put the acid to the, and he's collecting the CO2 in this container, and he's poured it in there. Can you see it's gone cloudy? And that's the clear lime water. So it's given off CO2. So that's, okay. April, what does aliphatic mean? The opposite of aromatic. How's that? No, aliphatic normally is the straight-chained, or it could be branch-chained, but not the benzene rings. Now, you don't have to do benzene rings in level 3 chemistry. You'll come across it at university if you do it then. So a lot of compounds have a 6-sided ring where every alternate carbon is double bonded. Well, actually every one is. So you get like a C double bond C, and then a single bond C double bond C, and it just forms that, and it forms a very flat ring. And that has a totally different chemistry. And those are called aromatics, and the other stuff is aliphatic. I've just tended to use aliphatics, just for anything at level 3. It may not have been the best description. Okay. Right. Now, remembering the terms of the leaving group, what we did in our first reaction lesson, that's very helpful in trying to work out the reactivity. So the acyl chlorides are the most reactive because it's got the best leaving group. OH minus, it comes off as a hydroxide. Here it comes off as an alkoxide, which is a much stronger base, CH3000 minus, okay? And I must admit, I don't know what that name is, a NH2 minus is a very, very strong base. So Cl minus is neutral, so it comes off the easiest. So in neutral solutions, which one of these 4 do you think are going to react? So 1, 2, 3, 4, or 1 and 2, or whatever. The first one. Okay, so this one reacts very readily, and you often don't have to warm it or anything. You may have to push it a bit with the others. In acidic solutions, though, can you see in acidic solutions, because these are bases, and you're making the conditions acidic, this will then come off as HCl. This will come off not as the alkoxide of OH, sorry, hydroxide of OH minus. It now will come off as HOH. And what can you tell me about HOH? Yep, H2O, it's neutral, it's water. So can you see under acidic conditions we can make these reactions work better? This will come off as an alcohol, ROH, and this will come off as a weak base, NH3. So you can still see that we've got increasing basicity as we go across, but they're not ultra strong bases that come across. And then in basic solutions, they don't react as well because you've got, these are still going to be the very strong bases. So basically I'm saying where they all break up in neutral solutions comes as chloride. In acidic solutions it's still going to be chloride, because remember, if it comes in HCl is a strong acid, so we'll break up into H plus ions and chloride ions, and that's why I've just made it there. And then the base, it also comes up as chloride because it's neutral. Yep, so Joe, under the right conditions, they could react. In other words, giving it a lot of heat and so on, or a catalyst. But usually, we would change the conditions to make it work faster. So, we don't want to heat something too much so it starts breaking down. So it's just much quicker to make them acidic. Okay, so here you can see it's quite a strong base, neutral. It will react with in basic conditions because it just comes off as an OH minus. Okay, and there's that competing acid-base reaction here. It depends with the ROH, but it really depends on if you've got OH minus. The alkoxide is, so these are the leaving groups. Yep. So April, what I'm just trying to show is under acidic and basic solutions, these are going to react much more readily than under neutral, which is green. And that's good to know, because when we talk about proteins and so on, why do acids and bases denature proteins? Why do clothes fall apart in acid and basic solutions if they, like polyester or nylon or something like that? And it's because the leaving group is more neutral, okay, and so will react more readily. And the amides, you also have those coming off as leaving groups. The reason being why this is still neutral is if I add OH minus, the alkoxide will grab a hydrogen off that to become a ROH, and the same thing with the NH2. Okay, so here's some examples. My acyl chloride with water forms straight away the OH, because can you see H2O is just HOH, and form HCl as well. But of course it exists as H plus ions and chloride ions. My acyl chloride with ammonia will form my amide and HCl, so nice leaving group as well. My ester. Now, so my ester under acidic conditions will form my carboxylic acid and also a neutral leaving group. And my ester under my basic conditions will form my carboxylic acid with the alkoxide, which is a terrible leaving group because it's so basic. But because we've got a lot of this base around, what happens when it forms this doesn't last very long at all, split second. What do you think that alkoxide is going to do to the acid? I mean, it is really shown there. It's going to attack and drag off that acidic hydrogen. Because remember, carboxylic acid is an acid. So if you've got a very strong base with an acid, it's immediately going to accept the proton. So we'll always have the anion and a neutral leaving group. So what I'm trying to stress is even if something doesn't really want to react under neutral conditions, under acidic and basic conditions, we can force it to react. Okay, esters and with water, I can put an ester into water. It's just going to float on top and basically not do anything. I've got to heat it, and some of it will degrade, but not much. Put some acid or some base in it, and it'll break up pretty quickly to form the alcohol and the carboxylic acid. And here with base, it'll form the anion and the alcohol. Okay, so what I've got here is this one's a good one to watch in terms of how reactive. You know, when I say, oh, you add it to water, it explodes. It's not an enormous explosion. What they're going to do here is they've got ethanol chloride in every one, and they add water and alcohol and so on to all of these so that you can see what happens. So there they're adding it up, and they do explain all along what's happening. So it's very good. You don't have to know too much of these, what we call mechanisms, so this don't worry about. At university you'll be doing mechanisms, but not at level 3. So yeah, so you can just see it shows them. Okay, can you see how it's fuming away? Because you formed HCl and they're reacting it with ammonia, so you can see that. Okay, I'm not going to go into that detail. I might actually just do it 4.2 minutes. Okay, can you see it's bubbling away there? He's added ethanol to the acyl chloride. So when I say it's explosive, can you see it's sort of reacting straight away? So it's grabbing, it's making an ester. The alcohol is reacting straight away with the acyl chloride to form the ester. HCl is given off, and that's what's shown by that white smoke. When you hold ammonia close to HCl, it forms that solid ammonium chloride. So that's that white smoke you see. Okay, so you can go through, I might do the amine because then you can see this white solid. So 7.9 round about there. Okay, so he's going to be adding an amine. Okay, can you see that white solid? So the moment he adds it, it forms that white solid. So the moment you form an amide, you're forming a solid. So that's a good way if you want to distinguish amides. You know, they're going to have a high boiling point, and that's because of that very high molecular dipole. Okay, so yeah, so I really, as I say, really recommend that you watch these, and if you find they're not listed in OTL, because I tend to forget what I've done, let me know and I'll make sure they go up. Or otherwise, frankly, chemistry is the person, although he's got lots and lots and lots of videos up. So if you don't want to plow through them, then just let me know and I'll put these up. So here's another one. This is with the carboxylic acids and SOCl2. And so you just see that reaction. Here it doesn't really show much, but again, if you react it with SOCl2, your products are SO2 gas and HCl. Now remember that quick test we did for the HCl gas being released is hold ammonia close by, ammonia reacts with HCl to form ammonium chloride. So that's the one test. And SO2, a quick test for that is it's a bleaching agent. They added like to dried apricots to keep them pale because it's a bleach. Yep, so there's just showing what's happening. And 1 minute 35. Oops. Okay, and these, I've got it too far. Okay, he's going to be adding. Okay, there he's testing for the HCl gas. Can you see all that ammonia coming, ammonium chloride coming off there? Just to show that some HCl gas is being formed, and you can see there's a reaction happening between the SOCl2 and the, and this is the bleach. Also SO2, if you think of, yes, yes, organic apricots tend to go much more brown, and the other ones are much paler. Yep, the sulfites, SO2 in moisture, it becomes a sulfite. So here's permanganate, purple permanganate, being reduced by the SO2. And do you remember this reduction equation from level 2 chemistry and also a bit of your 3071? You would have come across that. So as I say, all of chemistry, the more chemistry you know, it all relates together. So, okay, so that's good ones just to watch. Yeah, Joe, it is confusing if you're trying to learn it all at once. I totally agree. But once you sort of got one thing fixed in your mind, like you do know about oxidation reduction reactions with SO2 and permanganate, then it's easy to bring it in over here because it's something you already know. But if it's a whole lot of new reactions, it is very confusing. I do agree. Okay, so here they, you can see the amides being formed here. Okay, ammonia with the ethanol chloride, you can see that solid, just comes out. Okay, and you can see it's a very reactive reaction. So pretty much to react carboxylic acids, if you want to have esters, okay, then you form an ester with an alcohol and conch sulfuric. That is your catalyst. So you have to add some conch sulfuric just to get it going. It sort of primes the alcohol to start, it primes the carboxylic acid so that the alcohol can attack. Formation of amides is concentrated alcoholic ammonia. Again, you don't want your OH minuses around because then you're just going to get the acid back again. So you minimize your OH minus and you maximize your NH3. Acyl chlorides, SOCl2, and of course the formation of salt reacted with any base. Sodium hydroxide, ammonia, it's just a straightforward acid-base reaction. Okay. Now I've got here, why is it better to convert a carboxylic acid to an acyl chloride first and treating it with ammonia or alcohol to make the amide base ester? In other words, instead of going straight from a carboxylic acid to an ester or an amide, I first make the acyl chloride. Yep, it's a much stronger or quicker, and the reaction goes to completion with your acyl chloride, and you don't get that competing acid-base reaction. Correct, Johnny. So, and Joe, you had there because the Cl is neutral. So if you form the acyl chloride, what happens? You get a high yield, whereas if you've got carboxylic acid trying to form these, you get sort of, it goes in between. It's the equilibrium position isn't far to the right, so you've got to like keep on distilling out your product or something just to try and make that reaction. Yeah, Joe, well done. Okay, and it's because, as I say, it's this order of reactivity. So this will react better than this will react better than an ester, and the most unreactive is the amide. Okay, so amides are neutral, they're not basic because nitrogen does not give up its lone pair of electrons to something else because it's too busy sharing it with this carbonyl carbon because it's electropositive, and that's what gives it that big molecular dipole and makes it a solid. Okay, because instead of the lone pairs going for, you don't need to know it as a general priority order, but it sort of does help when you want to work out what's going to react and what's not going to react. You know, acyl chlorides react very readily. Amides don't. So you've got a lot more reactions to learn under acyl chlorides, and under amides, the only ones that you learn are how to form the amides and not any reactions amides do. So if you draw up your profile of your reaction scheme, you'll see actually there's none going from amides. There's only going to amides, but not from amides. Okay, not even acid-base ones. So those are the different types of reactions. Acyl chlorides, as I say, do all of them. It forms it forms esters, amides, and carboxylic acids. Carboxylic acids, you use SOCl2 to go back to acyl chlorides. Otherwise, you can form amides and esters, but not that strong. Once you get to an ester, you'd never be able to get an ester to an amide. Okay, you have to go back to a carboxylic acid or the acyl chloride before you can go to an amide, because the reactivity decreases. Now, polymers is quite a big section in that you will be guaranteed to get a question on polymers in the exam. In fact, one year they asked, I think, 2 or 3 questions, came up nearly every single time in each of the 3 questions, so it was a major component of it. So polymer is a type of substitution reaction, and we're looking at the condensation polymers. Last year you reacted alkenes to form polymers. Do you remember that? An alkene reacting, okay? Now, Joe, you wouldn't have done that, and you don't have to learn those are what we call addition polymers, and you don't have to know them for this year. Although I do know one year they compared condensation reactions to addition, because the assessment conditions do say they assume that a student is familiar with level 2 organic chemistry. So just be aware of that. Okay, yeah, it's maybe good just to go over it so you're aware of it. Like addition polymers, you have only CC bonds, so they are immune to acids and bases. Condensation polymers are not immune. Remember that's why I made such a stress about acidic conditions and basic conditions. Okay, so it's just adding H. Yeah, with alkenes, it's just when they combine, so that they lose a double bond because they're forming a single bond between the monomers. Here, it's condensation because we're condensing 2 together and we're getting a simple molecule being removed. Addition, we're not getting anything taken out. It's just adding together. Okay? Condensation, we're getting something taken away. So water, for instance, is a common molecule that's lost. Or if we're using acyl chlorides, it could be HCl that's being lost. Okay? Condensation polymers, we could either be making an ester chain, and we talk about ester links. So it's C double bond O O C. That's the ester link. So C double bond O O C. And this is the ester link. So you just look for the C double bond O O. There's the next ester link. So I've got here a snippet of a polymer having how many monomer units in there? How many repeating units? 3. So there's one repeating unit, there's one repeating unit, there's one repeating unit. Now notice I've highlighted this bond because this is the bond, remember, that breaks for substitution, not the OH bond. It's the CO bond that breaks. So if you remember a few slides back, the 2 different places where the bonds broke. Acid base is where the OH bond breaks. Substitution is where the CO bond breaks. So, right, so we can have that, or it could be an amide chain where it's C double bond O NH. So your proteins are this. Okay, so this is the basis of your proteins. And so your peptide link is your C double bond O NH. And again, you'll notice I've highlighted the CN bond because that is the one that breaks when I'm breaking up the protein, or that's the one that gets made when I'm making the protein. Okay, or the nylon, or the whatever it is. A lot of fabrics are based on these two polymers, ester links or amide links. Even things like Kevlar, which is bulletproof and so on. You put that in acid or base, and there you go, all your Kevlar's gone. Okay, right. So let's look at your ester links. So we can use as our monomers diacids and dichlorides. Diacids and diols. Or we can use hydroxy acids. In a single monomer, we have an OH and we have the carboxylic acid. So here's an example of a diol and a diacid. This could also be a diacyl chloride, so we'll have a Cl there and a Cl there. And remember, the concentrated sulfuric acid is used as a catalyst to make an ester. So we have that there. So what will happen is this O attacks as a nucleophile onto this carbon, and this OH gets removed, and it takes the red H with it. And it keeps on doing it. Okay, so that's why you've got ORO in red, and this in green, and there's your diol again, there's your diacid. Okay, these are all the new bonds that you formed. So when you are trying to combine, then just remember it's always your O from your alcohol that's being the nucleophile. And water is the leaving group. Correct. So each time an ester link is made, water is coming off. Yeah. Okay. Now, notice because sometimes they give you a protein and they tell you to break it up. So have a look at the pattern, the repeating pattern. Can you see this is O, C double bond O, followed by C double bond O, O. So it's like a mirror image sort of thing. Then we get the same pattern again. So when we get that where it's facing one way, then the other way, then this way, and then that way, it's made from a diacid and a diol. And okay, sorry, that was just to show where the links are. Okay, so there's my pattern. So O, C double bond O, C double bond O, O. Can you see it's facing in different ways? If I have a hydroxy acid, so a molecule with a carboxylic acid group in it as well as an alcohol, then I get this sort of pattern. Can you see it's always facing COO, COO, COO. So there are my ester links, sorry, and there if you want to break it. So have a look for those sort of patterns. And then it's just, if you can identify the pattern and you break it up, say, they say, here's this ester, and you treat it with acid, what are your products going to be? So doing it something like this makes you think about, am I going to form a hydroxy acid? So am I going to land up with one kind like this, or am I going to land up with two different substances, one being a diol and one being a diacid? Okay, so here's an example of an amide. So what if you treat it with base? Exactly the same. What will just happen, the difference between base and acid is your final product, and I will get onto that. I know we've only got 10 minutes on this lesson, so let's see how it goes. So we will, because that's a standard question that comes up, reacting something with acid, write the products, react something with base, write the products. And it's slightly different to what you get. You still break up the polymer, but your products are slightly different. So if I have the same thing, a diacid or diacyl chloride and diamine, so just like the diol, it's the same sort of thing. Okay, there's my peptide links all broken up. Okay, And if I get this pattern of NCO, CON, NCO, CON, okay, the NCO, CON, NCO, CON, I've got two separate starting materials, a diamine and a diacid. But if I have an amino acid, now amino acid has an amine group in it and a carboxylic acid. So if you've done biology and you've learned the 22 amino acids that make up proteins, do you actually learn that in biology? I'm not sure. But they can join together. So okay, you don't. So this nitrogen can attack the carboxylic acid of another amino acid, and that's just how the proteins are formed. You've got 22 amino acids, so there's hundreds of different ways that they can combine to give all these hundreds and thousands of different proteins to make your body do what it's supposed to do. So there's your peptide link, and when you break it up that way, you get con. Yes. I remember actually one year I did biochemistry at university, and we had to learn so many things off by heart. I don't think you have to do that nowadays. Okay, so here's an example. Because it's in a basic solution of a diamine, they've actually added some phenolphthalein to make it colored pink. And I'm just going to 2.18 minutes. As I say, you can watch the whole thing. So it's just pink because of the phenolphthalein that they've added. So what they've done, can you see they're pouring it in very gently down this rod. So can you see this is forming a top layer and that one's forming a bottom layer. So the amine is down here in the aqueous layer because it's pink, and the other one is up there, that's colorless. And the reaction occurs between the two interfaces, and can you see there's your nylon being formed. So you can just pull it out, and you can just there's lots of videos where people have done it in the classroom, and all the pupils carry this along and spread it all around the classroom. But that's how your fabric is made. Well, at least the cotton, or whatever you want to call it. Cotton is actually also another just ordinary polymer, but it's a natural one. So the sevacoyl chloride is dissolved in hexane, and that was that top layer, that colorless top layer, because remember that's neutral, so it wouldn't be affected by phenolphthalein. Why was it dissolved in hexane? Why wasn't it just added to water? It is actually fairly polar. Okay, it doesn't form hydrogen bonds with itself. It is fairly sevacoyl's got quite a few 6 carbons, so it's got quite a non-polar area. But what happens? Remember, this is an acyl chloride. What would acyl chlorides do when you put them in water? Explode. They don't actually really explode, but they will react with the water and give with lots of heat and give off the HCl. And what you're going to land up with then, instead of a very reactive sevacoyl chloride, you've now just got the acid version, which is a lot less reactive. Okay, and can you see this is now colorless because it's been washed, and because it's neutral, it doesn't retain the phenolphthalein. Okay. Right, now this is the tricky part, in that you are sometimes given different, so instead of breaking up a protein or a ester, you are given 2 amino acids and you asked to make different polymers. Okay, and students find this tricky because you've got to look very carefully. So say I use alanine and cysteine. Now, you do not have to learn these off by heart. You will always be told what the amino acids are. And you're told to make a link these together to make a di-amino acid. Di just means two, so an amino acid that's made up of two amino acids. So remember, each one of these has got a carboxylic acid and an NH2. So this NH2 can attack that carboxylic acid. So the NH2 of alanine can attack the carboxylic acid of cysteine, or I could have the NH2 of cysteine attack the C double bond OH of alanine. So those are my two dipeptides I can make. So here it's where the first one attacks. So can you see, when you do this, you've got to count. Okay, Caleb, how do you control that? Actually, enzymes. You would, I mean, your body does everything by enzymes. So it would be done, a lot of your biological stuff is done by enzymes, even in the lab. They actually, have isolated enzymes, and they get it done by enzymes. Okay, so when you draw this, so draw one like cysteine out first, and then go, right, my NH is attacked, I've got to drop an H. What's attached to my NH2? It's a carbon. So I've colored it red. You wouldn't actually have it red. So I've got to have a carbon. What is attached to that carbon? A methyl group and the carboxylic acid. So I must make sure I've got a methyl group and a carboxylic acid attached to the carbon that's attached to the NH group. So you have to count. A lot of students make errors because they don't count carefully. So just be very methodical. My N is attacking here. It's attached to a carbon, which is attached to a methyl and a carboxylic acid. So these the carbons attached to methyl carboxylic acid. And water comes off. Quite correct. If I have, though, the alanine, and okay, I've made this a different color for cysteine because I want to do the same sort of thing. If you're making your ammonia, your nitrogen attack over here, okay, then draw your alanine first. Okay, so my alanine I drew second there. Here I'm drawing it first. And now I'm saying, right, my nitrogen is attacking. The compound attached, the carbon attached to the nitrogen is attached to this sulfur methyl group and the carboxylic acid. So there's my nitrogen attached to a carbon which has a carboxylic acid and the sulfur methyl. So, sometimes students add in extra carbons, or they forget about a carbon. They might put this directly onto the nitrogen. So, oh, okay. Yes, so that's helpful if you do the HOH, and you're welcome to do it. Okay. Right, so do you think you can draw those things together?